Hello students, so today we will learn about hydrogen atom spectrum, which is a very interesting topic and sometimes students find it difficult also to understand. So let's start. In my last video, when I derived an expression for the energy of an electron revolving in an orbit in a hydrogen-like species, so that expression was ENH minus RHC into Z square divided by N square, where Z is the atomic number of the species, N is the energy level in which we are calculating the energy, R is the Rydberg constant, H is Planck's constant, C is the speed of light. So let's draw a diagram also. So suppose this is our hydrogen-like species and around it we have, this is an orbit, and we suppose we have one more orbit here. So suppose this is orbit N1 and this is orbit N2, and let's say the energy of the orbit are E1 and E2 respectively. Okay, so if we are particularly talking about hydrogen atom, so for hydrogen atom, what we will have? We will have atomic number Z is equal to 1. So the nuclear charge, which was plus Ze for a hydrogen-like species, that will become plus E. And if we put this, then energy value for nth orbit, it will be minus RHC divided by N square. And if you put the values of R, H and C in this expression and you convert the energy unit into electron volt, then if you remember I told this expression gives you minus 13.6 divided by N square electron volt. Okay, so this is the expression we will use today for hydrogen atom. Okay, so if we calculate the energy of the electron in the first orbit, E1, then it will be minus 13.6 divided by 1 square, it will be simply minus 13.6 electron volt. Similarly, for the second orbit, it will be minus 13.6 divided by 2 square, and it will be minus 3.4 electron volt. For the third orbit, it will be minus 13.6 divided by 3 square, and it will be minus 1.51 electron volt. And similarly, you can calculate this for 4th, 5th and 6th orbit also. So E4 will be minus 13.56 divided by 4 square, and it will be minus 0.85 electron volt. And E5 minus 13.6 divided by 5 square is equal to minus 0.54 electron volt. And similarly, at last E6 will be minus 13.6 divided by 6 square, and it will be minus 0. How can we divide this? Minus 13.6 divided by 36. So it is minus 0.38 electron volt. And similarly, if you are moving further, so energy at infinite, if you put n equal to infinite, you will get energy 0. And in the same way, we can calculate the energy difference between two successive orbits also. So if you are calculating the difference between first and second orbit, E delta E1 2, so this will be E2 minus E1, and this will be minus 3.4 minus 13.6, so this will be 13.6 minus 3.4, and you will get 10.2 electron volt. Similarly, you can calculate energy difference for second and third orbit also, delta E23, so it will be 3.4 minus 1.51, it will come 1.89 electron volt. And for third and fourth, delta E34 will be 0.11 minus 5 will be 6, and 14 minus 8 will be 6, so it will be 0.66 electron volt. For 4 and 5, delta E45 will be 0.85 minus 0.54, it will be 5 minus 4 1, 8 minus 5 3, so it will be 0.31 electron volt. And delta E56 will be 14 minus 8 6, and this will be 4 minus 3 1, 0.16 electron volt. And A infinite is 0, that we will take as it is. So if you notice here, as we are going away from nucleus, the energy difference between the successive orbits is getting lower and lower. So between first and second, the difference is 10.2, between second and third it is 1.89, almost 5 times smaller. Between third and fourth it is further smaller, between fourth and fifth it is much smaller, and between 5 and 6 it is the very low. So as we move away from the nucleus, the energy difference is getting smaller and smaller. So the energy difference between first and second orbit is the most, between second and third is smaller, third and fourth is further smaller, and so on. So let's draw the energy level diagram for hydrogen atom. And suppose this is our first orbit, this is n is equal to 1, its energy value is minus 13.6 electron volt. Second energy level will be quite far from it, this is n is equal to 2, energy value is minus 3.4 electron volt. Energy difference between these two orbits was 10.2 electron volt, but third orbit will be much closer to n equal to 2, this is n is equal to 3. Fourth orbit will be further closer, this is n is equal to 4, fifth will be much closer to 4, 6 is also very close, and so on, and very soon we will reach to n at infinite. So what was the energy level at n is equal to 3? This is minus 1.51 electron volt, this is minus 0.85 electron volt, this is minus 0.54 electron volt, this is minus 0.38 electron volt, and this is energy level equal to 0. Now this is the hydrogen atom energy level diagram. Now we remember the Bohr model of atom, Bohr's postulate. So if you remember, in hydrogen like species, the electrons can make a transition from a higher energy level to lower energy level, or lower energy level to higher energy level. But if an electron comes from a higher energy level to a lower energy level, in higher energy levels, electrons don't stay for much time, they stay for around 10 power minus 8 seconds, and they come back to lower energy level. So let's consider such a transition. Electron is coming from n2 energy level to n1 energy level, and when electron will come from n2 to n1, it will emit the energy difference between these two orbits, means delta E here, E2 minus E1, and this energy difference will be released in the form of a photon or quanta. And how much energy will be if the emitted photon has a frequency nu or wavelength lambda? This delta E, E2 minus E1, this can be written as hc divided by lambda or h nu. And we will get an expression for 1 upon lambda or hc upon lambda very soon. So here electron is making a transition from n2 to n1 energy level, and it is releasing the energy difference E2 minus E1 in the form of photon or quanta. Let's see how many transitions are possible for a particular energy level transition here. So suppose we have an electron which is coming down up to n equal to 1 level, means electron is returning back to n equal to 1, which is also known as ground level. So electron can come back to n equal to 1 level from any of the higher orbit levels. So suppose electron is coming down from n is equal to 2 to n is equal to 1, it can come down from n is equal to 3 to 1, 4 to 1, 5 to 1, 6 to 1, or even from infinite to 1. So all these lines I have made here, each of these lines is representing an electronic transition, and these lines are called, these kind of transitions are called Lyman series transitions, or these lines are called Lyman series transitions. Okay, so this is Lyman series. Similarly, the electron can come back from any of the higher orbit to n equal to 2 also. So such transitions can be represented like this. So this second series we have made here, where electrons are coming down from higher energy levels to lower energy level n equal to 2, these are called to belong Balmer series. Similarly, we can make another kind of transition where electrons come down from higher energy level to n equal to 3. This third type of transition series, this is called Paschen series. And if you go similarly, electron can come down to n equal to 4 from any of the higher orbit. This series is called bracket series. And at last, electron can come down from any of the higher orbit to n is equal to 5, and that series we call Fund series. Here P is silent, so it is PFUND, Fund series. So these many series we get in hydrogen atom spectrum. So they have a specific name. You should remember Lyman series belongs to those transitions where electron come to n equal to 1 from any of the higher orbit. Balmer series, electron comes to n equal to 2 from higher orbit levels, and in Parsons series electron comes to n equal to 3. In bracket electrons come to n equal to 4, and in Fund series electrons come back to n equal to 5 from any of the higher energy level. One more thing important to remember here is that Lyman series lines, they fall into ultraviolet region, so they are not visible. Similarly, in the Parsons series, these lines fall into infrared regions, so they also are not visible. And bracket series and Fund series, they belong in far infrared region, so they are also not visible. Only this Balmer series lines, they fall in visible region, so they are visible. And larger the line here means the line this where electron is coming from n equal to infinite to n equal to 2, that will have the highest energy. So larger the line, larger is the energy, and larger is the energy means higher will be frequency. So higher frequency means it is like blue end of the spectrum, and this is red end of the spectrum. So if you are told to find the lowest energy wavelength of the Balmer series, that means they are talking about this line. If they are talking about the highest energy line of the Balmer series, they are talking about this line. Also, the first line here we have drawn, this is sometimes called, in all the series actually, the first line is sometimes called alpha line, second line is called beta line, third line is called gamma, delta, and so on. Similarly, if you are told to find the wavelength of the alpha line of bracket series, that means you are being told to find the wavelength of this line. If you are told to find the beta line of Parsons series, that means this line. If you are told to find the wavelength of the gamma line of the Balmer series, that means alpha, beta, gamma. This line we are talking about. This is gamma line. Okay, I think you understood this. So let's calculate the energy difference for these different orbits. So as we saw that energy of electron in nth orbit, that was minus RHc divided by n square for hydrogen atom, because we put Z is equal to 1. So if electron is coming down from n is equal to 2, n2 to n1, n2 to n1, so, and the energy difference released will be delta E is equal to E2 minus E1, and if you put the values here, so it will be minus RHc upon n2 square minus RHc divided by n1 square. So we have put n2 and n1 in place of n in this expression, and you can take RHc common here, and it will be 1 upon n1 square minus 1 upon n2 square, and delta E can be written as Hc divided by lambda if the emitted wavelength is lambda. So delta is Hc upon lambda, and here you can cancel this H and C on both sides, and finally you will have 1 upon lambda is equal to R 1 upon n1 square minus 1 upon n2 square. Okay, so this is the expression for 1 upon lambda, and this 1 upon lambda is also sometimes called nu bar, which is wave number. This nu bar is called wave number. So wave number of a particular transition. So if you are talking about Lyman series, then n1 will be 1. If you are talking about Balmer series, n1 will be 2. If you are talking about Parsons series, n1 will be 3, and n2 can be any higher orbit. So you will put here. So 1 upon lambda can be found using this formula, and if you get 1 upon lambda, you can calculate frequency also. Frequency nu can be calculated by this formula, C upon lambda. So you just need to multiply this expression by C, then you will get the frequency 1 upon n1 square minus 1 upon n2 square. And if you multiply this whole expression for 1 upon lambda by h into c, you will get the total energy. So you can apply this formula for different series of the hydrogen atom spectrum. So I hope you understood this topic very well, and if you have any doubt or any question, you can post it in the comment section. I would try my best to answer those comments. So I hope you enjoyed this video. Thank you very much. Take care. Bye bye, and don't forget to subscribe my channel and sharing this video with your friends also. Thank you very much. Take care.